Welcome to the TOEFL Listening section. In this part, you will hear one or more conversations in an academic or campus context, such as a discussion between a student and a professor, or between two students. You may take notes while listening. Listen to part of a conversation. You will hear it only once, so listen carefully. After the conversation, you will answer questions about what you heard. Some questions will ask you about main ideas and details. Others will ask about implied meaning, speaker attitude, or how ideas relate to one another. Use both what is stated and what is implied to answer.
Good afternoon, Dr. Morales. I wanted to go over my project on reusable rocket technology and especially how recovery affects overall launch costs.
Hi Alex, that is a great topic. Start by telling me what aspects of recovery you are focusing on.
I am looking at different recovery methods, like propulsive vertical landing for boosters, parachute-based recovery for fairings, and mid-air capture of payload fairings. I am also trying to quantify cost savings and the trade-offs.
Good. Make sure you separate operational savings from manufacturing savings. Recovering a first stage can lower marginal cost per launch because you do not build a new stage each time. But there are added costs for recovery hardware and refurbishment.
Right. Could you explain the main engineering trade-offs when you design a reusable booster?
Certainly. One major trade-off is mass. If you add landing legs, extra propellant reserves and heat shielding, the vehicle becomes heavier. That reduces payload to orbit, unless you increase total vehicle size. Designers often estimate a mass penalty of around 10% on payload for a given design if you add return capabilities to a stage.
Around 10%? That seems significant. Does that mean reusability is not always worth it for all missions?
It depends. For high-cadence launch providers, reuse can pay off, because the fixed cost of production is amortized over many flights. For single one-off missions, the extra mass and complexity may not be justified. You must model reuse rate, refurbishment cost, and the number of flights per stage.
I read a case study about the Falcon 9 first stage being landed and reused. How does that example fit into these models?
Falcon 9 is a practical example of partial reusability. SpaceX recovers the first stage using controlled descent with grid fins and propulsive landing. Early on, they reported significant reductions in marginal cost per launch. Studies estimate that, depending on reuse rate and refurbishment burden, recovery can reduce cost per launch by between 30% and 60%.
Between 30% and 60%. That is a wide range. What causes such variation in savings?
Several factors. One is turnaround time. If refurbishment is quick and inexpensive, you get more flights per stage and greater savings. Another is reliability-related costs. If you need extensive inspections, non-destructive testing and component replacement, savings shrink. Third, the percentage of vehicle cost that the recovered stage represents matters. If the recovered hardware is a large part of the cost, reuse yields more benefit.
How do engineers estimate refurbishment cost and turnaround time? Are there standard metrics?
There are common metrics but no universal standard. Teams track time on wing for engines, number of thermal cycles, and probabilistic failure rates for components. They use maintenance man-hours per flight and parts replacement cost per flight. From that you compute refurbishment cost and mean time between overhauls. For planning, you also include logistics costs for transport, and any special facilities needed to inspect and certify a return stage.
What about aerodynamic controls during re-entry? You mentioned grid fins earlier. How important are they?
Grid fins are critical for guiding a booster through hypersonic and subsonic regimes. They provide control without adding too much mass. They must be thermally robust because they experience high heating during re-entry. Some designs use active control surfaces or reaction control systems as well.
And thermal protection. Is that usually reusable material or ablative?
Most reusable designs use high-temperature alloys, insulation blankets, and reusable tiles or coatings. Ablative material is easier to design, but it must be replaced after each flight, which raises refurbishment cost. So many teams favor reusable thermal protection that can survive multiple re-entries with inspection and spot repairs.
You also mentioned fairing recovery. How does fairing reuse compare to booster reuse in terms of cost-benefit?
Fairings are smaller and cheaper than first stages, but they are also non-trivial to manufacture. Recovering and reusing fairings can shave off additional cost per launch. Recovery methods include parachute descent and mid-air capture by a recovery vessel. The cost savings per fairing are smaller than for a first stage, but they are additive.
Are there design decisions that favor full vehicle reuse versus partial reuse?
Full reuse, where both stages return, is attractive in theory, but it increases complexity and mass penalties significantly. Many companies opt for partial reuse, where the most expensive stage is recovered. Choices based on payload targets, propulsion efficiency, and market cadence.
How do you include economic modeling in a technical paper on this topic?
You need a life cycle cost model. Include manufacturing cost per stage, refurbishment cost per flight, expected flights per stage, discount rates for capital, and probability of loss on recovery. Sensitivity analysis is important. Show how cost per kilogram to low Earth orbit changes with reuse rate and refurbishment cost.
One last question. If I recommend reuse for a small launcher, what should I warn a program manager about?
Warn them about the mass penalty, the need for investment in recovery infrastructure, and the possibility that high refurbishment costs can erode savings. Also stress that testing and incremental flight demonstration are essential to build reliability. Reuse is powerful, but it must be engineered with life cycle economics and safety in mind.
Thank you, Dr. Morales. That gives me a clear structure for my project and some specific numbers to test in my models.
You are welcome. Send me a draft and we can refine the cost model and the technical assumptions on mass penalty and refurbishment effort.
Listen again to part of the conversation, then answer the question.
If you add landing legs and reserve propellant for return, you incur a mass penalty that reduces payload by around 10%.
This concludes the conversation portion. For more TOEFL practice tests and study materials, visit Spinta.org.